So last week we stopped. I think we stopped here last week. So we'll be picking it up from this point this week. So yeah. So we'll be talking about indicator variables actually. So indicator variables or dummy variables are just like special type of binary variables. Essentially, you can convert like categorical variables to a number of indicator variables such that each level of the categorical variable is represented by its own indicator variables. So what we are trying to say is that, okay, you know, when we have like categorical variables now, okay, of this, we try to like create a new variable called the hours category, hours, the category of hours worked, right? So it was tagged as hours cat one. So hours cat one, we are trying to like partition the number of hours worked in such a way that each hours worked, like when we have benchmark for each hours work, like maybe lesser than, now in this case, so this hours category is one. It's like when hours worked is lesser than 40, lesser than or equals to 40, it gets one, but every other thing becomes zero. Every other hours worked, maybe it's greater than 40, it becomes zero. We doesn't really care about their category. We just want to know, we just want to create this a variable called hours worked, and in the hours worked, the data object will be, if the hours worked is lesser than or equals to 40, then the value should take one. If otherwise, it should take zero. This is what we've done here. And over here too, we said it's still the same thing. Like we create another one, we call it hours worked two. So that's like category two. If the hours worked is lesser than 60, if the hours worked is lesser than or equals to 40, it should take zero. If it's lesser than 60, lesser than or equals to 60, it should take one. And if it's like lesser than 80, lesser than or equals to 80, but not like lesser than 60, it should take zero. This is what we've done. So we created like multiples indicator variable, binary variables, like setting each categories into one and every other one zero for each levels, for each level of the data set. So that's just like creating a binary variable, but making it like in the indicator manners for the categories. So if you check this last one now, this last one is like hours category 4, right? And we state that if the hours worked is lesser than 40, it should take zero. If it's lesser than 60, it should take zero. If it's lesser than 80, it should take 80. If it's less than or equals to 80, it should take zero as well. But if it's greater than 80, it should take one. So just we are creating like a kind of indicator variables for the values, for all the values. So now we can now go ahead to like create a model. We can go ahead to create a model for the variables. So now you can see in this sense we use mental health as the response variable. The predictor one is hours worked. Predictor three, we exclude two. Predictor two, like two is hours worked three, and the last predictor is hours worked, hours category 4, right? So when you run this particular model, I'm coming, sorry, I need to run everything from up because this, yep, okay. When you run this particular model, you're going to have this model, right? You're going to have this model summary. So the question is now that how do you interpret this? It's still the same way we interpreted that, in this hours category one, you can see that because we know that we make every other we are going to interpret it with respect to the reference point, that when okay, say people that works lesser than that works hour lesser than or equals to 40 hours, yeah, has 0.3472 mental health score, like reduction in mental health score compared to order compared to the reference values. You have to know the reference values. It's just like, I know the reference value that in this case we use zero to represent orders, and one should represent people who work lesser than or equals to 40 hours. So people who work hours lesser than 40 or equals to 40 has a mental health score that is has a mental for no, sorry, I take that back. Okay, you say that people that like resident doctor that works lesser than or equals to 40 hours has 0.3472 reduction in the mental health score, yeah, compared to other groups. So you are comparing to the baseline. That's how you interpret this too as well. The category, you look at the category, how you code your variable. You look at this too as well, how you code your variable. That's how like you interpret it with respect to the reference. And this intercept like says that on average, like when every other predictors are zero, on average, a resident doctor has an average mental score of 24.27 on average, approximately. So, and what you want to like interpret again is the significance. You can see this is very significant, like people who work more than 80 hours. So this is not significant, this is not significant. You want to like interpret your r squared too. You can see the r squared is very low. It's very, very low. So you can see the adjusted r squared. So this adjusted r squared gives you like the number of, if you have like multiple variables. I will want you to pay more attention to the adjusted r squared. It gives you like how the model will change, like how the model, like the performance of the model will changes when you like include a new predictor. So yeah, and you can like interpret the F statistics, which give a broader view of the overall model. So I think this is where we need to start from. And we skipped a part last week. Yeah, I have my reasons for skipping that part. So I think it's a better time to talk about that. So I don't know if you get what I'm saying, or do you have any question before I go to the part we skipped last week? Okay, I'm going to take that for like everybody's fine. So now when you build a model, let me come up here. So we want to like regress mental health score against hours work, right? So once I run this line of code, like once I run this line of code, I summarize. So we want to assess the goodness of fit. So when it talk about the goodness of fit, so it tends to like tell you if your model is viable enough to like make predictions for the random phenomenon you are trying to like study. Yeah, so you want to check the fitness of the model. So when you are checking when you like plot, you use the plot function for the model. You are going to have 4 plots. This is 1, this is 2, this is 3, this is 4. So this 4th plot tells different story, and it is this story you are going to like try to like explain the behavior of your model, if it's actually significant, if your model is good enough to like make some what are they calling, is good enough to make some prediction, some reasonable prediction. So, and if there is if there are problems, you have to like address the problem. So this is the residual versus fitted plot. This is the residual versus fitted plot. Once you like use the plot function and you pass in your model, the model you built, right? You pass it into the plot function. You're going to have these 4. You're going to have these 4 graphs. So this is the first one, residual and predicted values. So we know from regression that regression has some assumption of like error term, which is the residual errors. They are normally distributed with mean of 0 and variance and constant variance. That's which is sigma squared. That's like that. So now we want to like, what we are trying to do now is like a residual analysis to see if our residual does not violate the assumption of a linear models. So now, and if you are trying to like check the goodness of fit using this residual versus fitted plot. This is the fitted on the x-axis, which is the model, predicted model, and this is the residual analysis. So there is a way they calculate the residual manually by subtracting some stuff. You get the residual analysis. So you now plot them against each other. You can see, you can see this. I'm coming. Let me try to like find. I don't know if I can use. Can I use this? No, I cannot. I would have loved to use marker, but I don't think I have access to like you can using a marker. You can see like a line at the when you on the y-axis when it is 0, you can see like a kind of dash line across the graph. So when what you have to watch out in this place is that this line is called 0 line. Yeah, it's called 0 line, and some people call it residual equals to 0 line actually. So all your predictors, like this red line, this reference line, must be very close to this 0 region. But in this case, should we say this is kind of close? We can't really, because sometimes visuals can be very, very deceiving. But we can actually say maybe approximately kind of close, but not too close like that. But it's close. It's not really deviated. It's not really far deviated from it. It's not really like it's not far really deviated from it. So this is what you want to check. You want to check if your if the red line, if the reference point to the red line are approximately 0. Yeah, because I think it must be very closer to 0. It must be very closer to 0. So if you have that conviction that, oh, this red line is very closer to 0, that gives you like a part that my residuals are behaving like they are like behaving up to the assumption, like the assumption of linear models. So we have the QQ plot. What did QQ plot say is that because part of the assumption is that the residuals are normally distributed. They are normally distributed, and QQ plot is used to like check the normal distribution if a data is normally distributed or not. So this, you can see this dot line moving upward in an upward manner, like from the left hand side to the right side. This like dash line like that. These are the dash lines. I know. So this your point. This your residual point should like follow this pattern. Should follow the line. Not sometimes it can be on the line. If you check all from this region to this kind of region, they are on the lines. So it's deviated a little bit from here, and it's deviated a little bit from here. So these 3, 2, and 1, they are outliers. So these are outliers, which you might want to remove it in your data and correct the outliers using some I think some correcting measures like that, maybe trim function and all this kind of stuff. You can correct all those ones. So now this shows that this our residual is kind of normally distributed. Yeah, comes like it's normally distributed. So that shows that the assumption of normality of the residual is not violated. Because if it's violated, we have to find a way. Maybe we transform your model. I think there is this portion in the next couple of like slides. We are going to see where we talk about transformation. So where if it violates that, you transform your model, kind of. So we have this scalar location plot, like scale location. So it's plus the standard residual, like the square root of the standard residual against the predicted value. So against the predicted value, this actually talks about the constant variance. You know, we have constant variance. I think you can use this one to like now to like make decisions concerning regarding constant variance. Actually, some people use this to make decisions regarding constant variance because, well, let's use coming. Okay, if you want to use this to make decisions about constant variance, you have to like have all your points. You have to have all your points not showing any patterns. They have to like be very scattered around the 0 origin. They have to be very scattered. They will not show any patterns. This is kind of showing some kind of patterns, but the patterns are not really clear like that. But when it's showing patterns, I think I let me try to like find something to show you how residual work. Residual plot. for the variance. Yeah, this is the perfect example. I don't know if can anybody see my screen? Jesus.
Yes, I can.
Okay, okay. Thank you very much. Thank you. So if you look at these plots, can you see like they are really scattered? They are scattered around the reference line 0. But when you have like a kind of pattern, it can be like a kind of U shape, or you have like this curve like that, or is having one weird pattern. That shows that what are they calling? That shows that the variance assumption, which is supposed to be constant, like constant across all residuals, is really violated. Is violated. So this residual versus Leveren position, you can use this to like determine high inference points in the data. So if you check this and this actually gives you like high inference points that you have to like, you if you want to deal with them, there is a way to deal with them. Like you check if it's like very extreme high inference points or very low high inference points. If it's very low, you can leave them. If they are very extreme, you can remove them, kind of. So this gives our high inference points. It tells you if there is outliers in your observations and all those kind of stuff like that. So these four plots are very, very important. Most especially this one that talks about the constant of the variance, and this one that talks about the normality of the residual. So they are very, very important. You can check all these others too as well, because this high inference point, because if you have like some outliers in your observations, it might affect the way your predictors your predictions behaves. So you might want to like amend, like account, like adjust the outliers. There are ways to adjust the outliers, maybe dropping them, like there are ways to like address that. So that's what we skipped last semester, last week. So now we'll be talking about multiple linear regression. Before I move forward, is there anything regarding the plots that you want to ask? Is there anything regarding the plots?
Yes, I had put a question in the chat asking you to define exactly what residuals are and what they mean.
Okay. Okay, let me zoom. I think the last time we have to zoom out, right? To zoom. Can you see my screen very well? Because I'm trying to like zoom out. Let me stop sharing so I can zoom properly. Stop sharing first. Thank you very much. So, you asked me to like define what residuals are. Well, theoretically, how will I say it? Um, Residual is just like the difference between your actual value and your predicted values. Your actual value and your predicted values. That's what residual means. So let me use this as example. Your actual y value, like your actual response value and your predicted values. So now we know regression models to be like repeated regression model to be like y hat equals to b naught plus b1x, right? that is your fitted model. Like that's the model you are fitting. So now when you get a particular estimate for beta, okay, let's say we get a particular estimate for, let me go back to this example so I can use this. Okay, so now we are going to have this as our beta naught and this as our beta 1. These are the estimates, right? You have to like get your fitted value. So you try to like you have like your response variable again, which is your y hat, equals to this intercept plus no, it will be negative because this sign is negative this coefficient here into brackets. You have x variable, right? That x variable we take the number, the actual value of x in the data set. That's how to get your fitted value. So now once you get your fitted value, to now get your residual, you subtract your actual value of y from that fitted value. That's like your residuals. So you subtract them. Once you subtract them, that's your residuals. So statistically, the sum of your residuals, like the mean of your residuals, should be 0. It has a mean of, it should be 0. It will never be greater than 0. So and I can show you that from here. This we have a model already. So if I write model 2, right? $sign, you are going to see all things that I have values, I have access to, right? This these are my fitted values that I've explained that you have to take the coefficients and put the actual value of x across the data set. You have to, this is your fitted value. So let's do something. Let's do mental what's the data set we are working with? Okay, RDS2, right? So it's mental health score minus model fitted value. I want to show you something. Model fitted value, right? Let's do this and see what it gives us. Let's find the mean. Can you see this is 0.0000000 something? That is approximately like 0. If I round it into 1, let's see what happens. Round into 1. This is 0. So this is 0. And if you check your model, like your model summary, like model 2, right? And you use the $sign, and you actually pick the residual, and you like find the mean of the residual. The mean, like let's just say the mean of the actual residual from the model is going to give you the same what you get. And if you like round it to be 1, what are they calling it? Is it 1 decimal place? We are going to have 0. So that's how your residual is like the difference between your y observation, which is your response observation, your response variable observations, and the fitted values from the model. So do you understand that?
Yes, thank you.
Okay, so it's that residual. Is that residual that we use? Some people call it error terms. Is that residual that we use to like check for those plots, like see, because there are assumptions regarding that residuals, which is 1, it must be normally distributed with mean of 0 and variance and a constant variance. So is the constant variance you want to check with this plot? Are the variance, are they behaving constant? Like if they are not behaving constant, you are going to see it. It's either you see some funny patterns, either it has a U pattern, a V pattern, or you see it moving in a way. But when it's scattered around the 0 origin, then it's scattered around them in a clustered manner. Like that shows that the the assumption of constant variance are not violated. So is there any question again? Okay, I'm going to take that for no, right? So please, I can't see the chat box when I'm like presenting. So in case if anybody have a question, you can just like unmute, like so that I can, because I don't have access to the chat box when I'm trying to like walk you through the stuff. So now we have multiple linear regression. So Multiple linear regression is when you have more than one predictors or covariates. Yeah. So there are a number of reasons why we may want to like have multiple predictors. Which one you can want to have multiple predictors to like improve the model? Maybe let's say we consider mental health score and the hours worked. We want to see the behavior of we want to predict the actual hours worked based on the mental health score. And we notice that our R score is very low, which is telling us that there are some variables that affect mental health scores that we have not considered. So we are not trying to like, oh, let's consider this model, maybe the number of children. When people tend to have children, they stress themselves mentally and all this kind of stuff like that. We want to see the effect on the the mental health score and all this kind of stuff. We might want to include that too as well. So we might want to like include that too as well. And we might want to like, if we include that, it's going to improve the prediction. And we might want to like adjust for confounding variable. What confounding variable means is that a variable that has relationship with both the dependent variable, that's the response variable, and the independent variable predictors and the predictors, that's confounding variables. We've worked on this assignment or this one already. So now we want to like make adjustment for like this model by adding female. We have a female variable in the data set. So this female normally ideally is like gender. They just name it female, is gender. We want to see if what happens if we like put sex in the model. And I want you to take note of something. Can you see the R square? Why we did not consider including sex in the model? But when we put gender in the model, can you see what happens to the R square? It slightly increases, right? I think so. It slightly increases. Yes. It slightly increases. So it's like improved the model. So now, why we put gender, which is sex, into the model, gender into the model. So now what you need to actually know is like you need to know how you code your variables, because if you do not know how you code your variables, it's going to give you a lot of problem interpreting this. Let's assume like 1 is for female and 0 is for male, right? In this context of this gender now. So you've interpreted this that on average, when the hours categorical worked is held as constant, and the gender too is held constant, which is 0, the average mental health score for a resident doctor is 24.31. Let's just leave it like that. So you've interpreted this with respect to the reference. You've interpreted this with respect to the reference. You've interpreted this with respect to the reference. So now we have this female. Now we said 1 to be female and 0 to be male. You are going to like interpret this as like, okay, for any female resident doctor, for every female resident doctor has a mental health score, of 0.1203 lower than that of male. That is, down for every female resident doctors, their own mental health score on average is normally lower than their male counterparts by 0.1203. So this is a multiple linear regression because we have the hours work in categories and we have the genders. So I don't know. Is there any question? Do you want me to like come again? How to interpret that is that you interpret it with reference to the with reference to the reference point, which the reference point is the male category, which is 0. So for every female resident doctors, they have a reduction in like their mental health score compared to their male counterparts is reduced by 0.1203. That is, they have 0.1203 reduction in the mental health score compared to their male counterparts. So their male counterparts will have this coefficient more than them. Like they are going to have 0.1203 mental health above the female resident doctor. So is there any question regarding what I just said? Any question? Okay, no. I believe we get that. So now you have to like take cognizance of the p-value, the p-values as well. This is not significant. Actually, it's not significant, but this is significant. This is not significant. This is significant. So you have to take like you have to like take a look at the R square without the female versus when the female is there. It improves by when we add it. So it leads to higher R square, which improve the model. It improved the model, but it improved the model, but the variable we included does not mix. It does not really, it's not significant actually. So now we want to do another one by adding the number of children they have to the number of children. This number of children now, we treat it as a continuous value because we treat it as a continuous values. So in this case now, you are going to interpret this for one unit, like for one unit increase in the number of children, like if one of the resident doctor have additional children, their mental health score reduces by 0.0548 when other variables like hours worked is held constant. So if you check the p-value compared to, if you check the R square compared to when we did not include the children variable, you can see this is more higher than that. This is more higher than that. So again, this is a continuous value because we did not make the children variable categorical. So you say that for every unit increase in the number of children they have, the mental health score of the resident doctor reduced by 0.055. So that's that. So we can also like try to like create a categorical categorical. We can like make this number of children categorical instead of treating it as continuous, and let's see what happens. So we said if the number of children in the element is this, you should take 0. If the number of children in the element in the children variable, you should take 1 and 2, like that. We are creating a kind of it's just when you use if else, if this, if the number of children is 1, then equals to 1. If the number of children equals to 0, equals to 1, if otherwise, that kind of stuff. We've talked about this, how to like create this kind of variables in our last class. So it's very straightforward. It's very straightforward. So when you run this model, you can see this model now. We have mental health, we have hours categories 2, 3, and 4, and we have number of children cat. This is child cat. So if you run this, we are going to see that this creates this now is different from what we have. It's different from what we have here. It's different from what we have here because we need to like interpret. Sorry, it's different from what we have here. So we need to have like interpret it with respect to the reference point actually. So this shows that resident doctor who has children, who has a child, has a 0.1107 reduction in the mental health score compared to their counterpart that does not have any children. Compared to their counterpart that does not have any children. So that does not have any child. Sorry, that does not have any child. If they have a child, they have this amount of mental health reduction compared to their counterparts. So, and if you check the R squared, it increases, and also so instead of like doing this, like this now, we just like try to like make category for all those that have children. We just like make conclusion for them. But if we want to see the impact of the number of children, Like if someone has 0 children, if he has 1 child, no, sorry, if he has 0 child, if he has one child, if he has 2 child, if he has 3 child, like we want to check the impact on the mental health score. So we can come back again, to you can reassess, we can like you are going to treat your categorical variable as the categorical variable we've created earlier. You are going to treat it as factors. So if you treat it as factors and you run this linear model, what you are going to have is you are going to have this. So it's going to give you for each number of children categories, the mental health score reduction that the resident doctors have. So when you check this, you are making this to reference point 0 to someone that does not have the number of that has 0 child. So now for anyone that has like 1 child, so have a 0.897 reduction in the mental health score compared to someone that has 0 child. So now for resident doctor that has like 2 child, they have 0.62 increase in the mental health score compared to their fellow counterpart that does not have any. So people that have 3 child, like 3 children, sorry, where am I? 3 children, so they have like negative 1.1. They have 1.10 reduction compared to their counterpart that does not have any. So, and if you check the R square, you can see that the R square actually increases. It increases compared to previously that we have 0.000 something like that. But if you check this, they are not significant. They are not really significant. So they're not significant. So now we have something we call model comparison. We have something we call model comparison. You see, we've built like multiple models. We've like checked mental health scores on hours worked, child, sex, and all this kind of genders and all this kind of stuff like that. So you need like one interesting model. That is where AIC comes in. ICAIC information criteria or criterion. I think that's how they call it. ICAIC information criteria. So it tells you which of the models, like which model work best. So now let's retract our step back to model 5, model 4, and model 7. Comment was model 4. So in model 4, we regress hours worked, hours category 1, hours category 3, hours category 4 on mental health score, right? Let's check model 7, model 7, model 7, model 7, model 7. So, and in model 7, we regress hours category 2, 3, 4 plus the number of children, like the like effect of children on mental health. So now let's go and compare the two models. So there is this function in R called AIC. Once you just say AIC, so then you pass the models into it. Model 4, model 7. Let's see what it brings. So it's going to give you this AIC. You have to pay attention to this AIC. We have a principle they called, I think, parsimony's principle. We say that when you have two competing models, the model with the lowest AIC or BIC take precedence. That is, the model with the lowest AIC in this case is the best model. So when you check between these two models, this AIC is 836 and this is 821. So according to the parsimony's principle, this model 7 is more viable and is more statistically sensible than this model 4. So that's what we use AIC for. We use AIC to like compare model and to know the model which makes sense. So that's how to like use AIC to like select what are they calling, to select to select the model. So you see that the smaller, so we can here we see that the model 7 has the smaller AIC. So we often use the thumb rule of 10 actually. Need to confirm, but when you just compare the two models, the one with the smallest AIC take precedence. Yeah, it takes precedence. So and also you don't have to be very ignorant of maybe what is happening. You don't have to be ignorant of what is happening. When I mean you don't have to be ignorant of what's happening, is that if you are using AIC, you have to like consider the R square too as well. You have to look all those things. So because sometimes maybe one has a better AIC, but does not have a very good R square. So you have to check all those things to know what happened. You should check what is happening in the model before like concluding that, oh, this is the best model. This is the best model of fit. So now we go ahead to like create adding multiple covariants, like by adding we have the number of children in categories and the age categories. So when we summarize this model, you have this result. So now you are going to, on this intercept now shows that when all of these predictors, when they are 0, this is the mental health score of the resident doctor when all the predictors are 0. So now you have to like interpret this with his own reference point. You have to interpret this with his reference point that the number of children they have determines their mental health score. So for someone that have one child, there is 1.1 reduction in their mental health score. So for a resident doctor that is between 30 to 34 years of age, there is 0.404 increase in their mental health score compared to someone who has of lesser age, maybe compared to someone who is lesser than 30. So you have to like know the reference points you are interpreting it with respect to. Is this someone that has age lesser than 30? So you have to know all this kind of stuff. So and you can still do your comparison of model again. Once you do it, you can see the model with the lowest one. After even adding more predictors to this, the model 7 still like supersede like model 8 using the AIC method. So now we have the interaction effect. So before moving to interaction effect, I don't know, do you have any question before moving to interaction effect?
There's a question
Yes,
in the.
I have a.
Go ahead.
Okay.
I was gonna ask, what do you do in a situation where the AIC and the R squared are giving you different different conclusions about the best model?
Yeah, in my own sense, I think AIC, when it comes to like selection of model, I think AIC supersede R square kind of. I think so. Yeah, in my own sense, actually, I think AIC supersede the R square, because the R square just only tells you when I say good, like tells you the variation, like the variation in the dependent variable, which is mental health score, that can be explained by joint effect of the predictors. So, but you can use that to make your decisions too as well, because you want a model that has like I is the coefficient of determinations, but the AIC tells you which model is actually best in all the models you've highlighted. So I think you should like stick to the AIC approach of like selecting models. But if you are sticking to that, you don't have to like be ignorant of R squared too as well. You have to be very conscious of the R squared.
Okay, thank you.
Yeah. So now we want to move to interaction effects actually. So adding like trying to like put interaction in the model, So there are different reasons why you can put interaction to the model. I think to the best of my own understanding, if there is relationship between two predictors, we might want to check the interaction effect between between two of them. There might be other reasons actually, but the one I'm mostly familiar with, if there is multicollinearity within two variables and two predictors. Like, let me see, we know we have these our predictors. So maybe there is relationship between hours work in categories and the number of children. There is relationship between them. There's high correlation within them. But I want to check the interaction effect if we don't want to drop one of the variables. So that's one of the reasons, like, for adding interaction effect. There might be like some other reasons. So now, taking for example now this model. So this model now, we don't have any interaction effect in this model because this is just like we regressing age hours worked in categories and the number of children in categories and age in categories against mental health score. So let's now look at where we had interaction effect. If you check this, we did not put plus, we use multiplication. But when we were trying to like do this, we use plus. So if you are using plus, then you are just like building your normal regression model. But when you are like, when you add multiplication to this, then you have already, like, you are telling her that, oh, I want you to like check the interaction between the number of children in categories and the category and the age categories, the interaction between them, the interaction effect between them. So you have to be very careful when it comes to interpreting, when you want to interpret interaction effect, actually, which myself, I will be very, very careful. So now we know the intercepts still remain the same when other predictors, when they are zero. On average, a resident doctor will have a mental health score of 24.19 thereabouts. On average, we have that. So you have to interpret this with the reference point. You interpret the hours category when it's 2, when it's 3, with the reference point. The number of children too, you interpret it with the reference point, which is 0. The age category, you interpret it with the reference point, which is 0. So now, what I want you to take notice of this is, we see when the number of child is 1, when they have one child, right, and their age is within 30 to 34. Can you see? The resident doctor, when a resident doctor have one child and the age, the resident doctor age is within 30 to 34. So they have this hours, they have this what are they calling? They have this mental health score reduction, but they have it on this and where is it? On this and where's the one? Oh, we did not add. Okay, on this and this. I don't know if you get. You've interpreted this with respect to someone that has that does not have children, right? Does not have any child. You've interpreted this with respect to someone that have like lower age than 30, right? So interpreting this says that, oh, for every resident doctor that has one child and falls within the age of 30 to 34, has a reduction of 9.92 in their mental health score, on these two values, because they still falls in these two values as well. They still falls in these two categories. So you have to be very, very careful. To my own best of understanding, that's how I know I can explain this. I don't know, Dr. Abiy, I don't know if you can like if you have a better way of explaining that, because that's the best way I can explain that.
No, so that's exactly correct. The way you will interpret an interaction term is that you will add up all the terms that include that interaction term as well as the base term. So if you project your R code again, sorry. Right. So just as you were explaining, so if someone asked you, so the reason why we do interaction is to assess whether the effect varies in one group versus the other, like Daniel was saying. So if we wanted to see whether the effect of having children on mental health score varies by the age of the resident doctor. So you want to see whether people who are in their 30s versus those who are in their 40s, whether if they have children, that the effect of having children is different. So this is a little bit, you're going one step more. And so to be able to look at that, you would look at each of the terms. So for instance, if we wanted to see without interaction term whether someone with 3 children has worse mental health score, we would look at that line for as factor with the 3 at the end for children cat with the 3 minus 3.861. But if we want to see whether their age impact them, then we will have to also look at the set of interaction terms with age inclusive. So now for someone who is 50 to 40, it's not on the screen. For someone who is 40 to 44 years with 1 kid, that will be 1.658 plus, right, plus the age category in question, right, for 40 to 44 years, minus 8.29, plus the children category, then plus it's a little complicated to calculate it by hand, but good thing that we have computers that can help us do that. So if we're not showing it in this code, but if you needed to calculate what the effect will be for a specific age category, then there are R packages that will help you do that with an effect function. You'll be able to see, it will become very simple. And maybe we can demonstrate this in a future class. And that way you can say, oh, when comparing age category at, like I just explained. So essentially, like Daniel said, you have to add the beta estimates for the interaction term with the beta estimates for the fixed effects, which is the hours category, age cat, blah, 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 along with the intercept to be able to get the predicted value for that effect modification. I don't know if that helps or if I just complicated it further.
Thank you very much. I think that that's very insightful actually. So thank you very much, Dr. B. So you have to check the R square too as well. But these are NAs over here, so you just have to ignore them for now. Yeah. So I know there might be a way to adjust that, but for this class, you just have to just ignore that and just So you try to this is the R square, then the adjusted R square, the F statistics, which deals with the overall significance of the model to see if the model is significant or not. This is so you can see the model is significant. So yeah, and comparing this to model weight, between model 8 and model 9, you can see what are you calling this model 8 outperform model 9. That model 8 is more is best, model 8 is the best model among the two models. So now we want to talk about non-linearity actually, non-linear models actually, just briefly, because we are going to use this simple linear regression where we regress hours worked on mental health score. So let's run this model. So we have this question, right? So there is this stuff. I will go back to this place. This particular place I explained. I explained when we are assessing the goodness of fit actually. Ideally, the only time you tend to believe your model is not linear is when because the only time you have to believe they are not linear is when the assumption of equal constant variance is violated. That's it. Maybe you check the residual plot, I see you're seeing some kind of patterns. Maybe you see kind of a U shape in the variance. You are seeing maybe a kind of the plot are not really scattered around zeros, which shows it has constant variance. So that is when transformations comes in. So that makes the model to not be linear. You have to maybe you have to take the log of the response variable. or you take the log of the predictors, or you can take the square root of the response variable, or you take the square root of the predictors. Am I? Yeah, yeah. So that those are what you try to like do to like, oh, you transform so that you are going to make adjustment to that. And when we talk about non-linear, like non-linearity, non-linear models, this is when maybe you are taking let me see, you want maybe your predictor, you are squaring your predictor. Like this model now, you want to like build a model of like hours work squared. So a linear model is like, it's very linear. It does not have like maybe square root. It does not have it's just like linear. But when you have like square, cube, it changes from like a linear model to like a kind of to a non-linear model actually. So you have to like watch out for that. If you see that your residual plot is behaving kind of somehow, you can come and transform your model. So in this case, we are trying to like regress the hours worked and the hours worked squared. So we create a new variable called hours worked squared, which is we multiply the hours worked times 2. Like we multiply them times 2, then we regress them as model 11. So you can see the coefficient over here. So you can see the coefficient over here. So that's like literally what non-linear linear model means. So when you regress, when your model is not linear, you're having like, you are taking one of the predictors, you are taking the square, you are taking the square, like you are taking the square of its values, or you are taking the cube root of its values. You are trying to, that is not linear. So
Sorry, Daniel. I was wondering if I could, because I know the class is coming across this concept of non-linearity for the first time. Perhaps I could just quickly share my screen and show what these curves look like,
okay.
so that we can maybe ground a little bit. I suspect that this will also come up in class, but I just wanted to give a quick illustration. Sorry, now I can't find it. Just search. But I'll just share my screen. All right, can you all see my screen yet?
Yes, we can.
Okay, all right.
Yes.
So basically, when we are doing regression models, right, we're expecting, maybe let me show you. We're expecting to see lines that look like this, right? This is the traditional where one variable is on the x-axis, one variable is on the y-axis. This is the independent variable on the x-axis, the dependent variable on the y. So as one goes in one direction, so in this model, for instance, this one on the edge, sorry that I'm doing this very scrappily, as the independent variable increases, the dependent variable decreases, so the beta estimate for this one will be negative, right? For this one that is in this Wikipedia, as the independent variable increases, the dependent variable also increases. So the beta estimate for this will be positive, right? I don't know if this is an intuition that you already got from the class, right? But when we start talking about quadratic, we might be assuming that, because if you think about it, not all relationships in life actually follow that straight line going upwards or going downwards that linear regression assumes. Okay, in real life, especially in biology, also, just humans in general, we are not necessarily our interests are not necessarily consistently going in one direction. Many things come into play. The same thing with in biology, right? So it doesn't necessarily mean that as a man gets older, his blood pressure gets older. It gets higher, right? So you might assume, if you do linear regression, you might assume that you might assume that as blood pressure, as a man gets older, his blood pressure increases, but that's not really true, because it won't increase monotonically like this. It might increase and gradually become, like, the increase might get slower. And so what we're doing in non-linearity is trying to actually follow the truth to the extent possible. So we're allowing the relationships to curve, right? So we're going to get curves that looks like this. This is the quadratic, and this is when we add a square, right? So we add a square to one of the terms. If we go back to quadratic formula in math, this is basically what we're trying to do. It might be like a curve going upward like this, where we're assuming that maybe as a relationship, maybe as age gets higher, the blood pressure decreases and then it starts increasing, right? This is the assumption of this curve. Or you might have a curve that looks like this, where as age gets higher, the blood pressure increases, and then after some time, the increase reduces. So as I don't know, it keeps, but this one shows that it then keeps, the increase reduces, it doesn't go as high. So it doesn't necessarily mean that you're going through the entire spectrum of the curve, but you're allowing the relationship to curve in the manner of a quadratic equation. And that's the same thing for a cubic, where we add a cube, right? So we add the cube to the formula, like Daniel was just showing. It means we're allowing the curve to, we're allowing the relationship to curve more than once, right? To wiggle. That's basically what we're seeing with these cubic formula. So what we really are trying to do here is we're assuming that we don't know what the true relationship is, what the shape of the true relationship is. We always start with a linear relationship. In linear regression, we assume that there's a straight line monotonically increasing relationship, or monotonically decreasing, but that's not always true in real life. The relationship often curves. And so we want to understand whether the straight line, does it explain the relationship, or does the curve explain the relationship better? Okay. And so when we now include these terms, these polynomial terms, into the regression equation, we will compare it with the straight line using the model comparison that Daniel was just talking about, AIC, right? Or the other forms, and we'll see it as we go. But once we then use AIC to compare, if the AIC is lower for the linear relationship, then it means that that relationship is not really curved. There's no curvature, right? If the AIC is lower for the quadratic, then we will assume that a quadratic relationship better represents the true relationship than the linear, than the straight line relationship. Or if the AIC is lowest for the cubic, right, then we will assume that that cubic curve is better represent the relationship than maybe either of the quadratic or the linear. And it's always good when you are doing linear regression and your independent variable, the independent variable is continuous. It's always good for you to test non-linearity. Thank you very much, Daniel. If you have any questions, I'll take them as we go.
So, is there any question? Okay, I think there is no question, Dr. B. Thank you very much for sharing that. So, I think with that we have I'm coming. Let me check. Okay, do we still have any other stuff? I've tried this. We've done this. So by comparing, we've compared the model. We compare model 10, which is like the normal linear regression model, against the non-linear regression model. And you can see that the non-linear regression model take precedence using the AIC rule, like AIC, the IKK information criteria. So like if the quadratic, like if you take a quadratic variable, like you use the quadratic variable and it seems to be not is not significant, you have to like take a step further by taking the cube of the variable actually. So which we try here, we take the cube of the variable to see what happens. So like we multiply the hours work 3 times, cube, like raised to the power of 3. So we regress that against we regress the hours worked, the hours worked square, and the hours worked cubed against the mental health score. So, and we use AIC to compare this against model 10, which we still see that the new model, like when we take the squared, the hours squared and the hours cubed, still take more precedence than the normal linear models. So is there any question, because we come to the end of this particular section, our lab 4? Is there any question? So I'm going to take the silence for no. Okay, so now we are moving to our lab 5. So which might be my last time. I'll be seeing this, be like taking this particular section. So so now we'll be talking about chi-square. Chi-square and logistics regression.
So
Sorry to
Daniel, can I ask
interrupt.
that we only go through chi-square because we have not really taught logistic regression in class?
Oh, okay. Yeah, that's fine. So then maybe my face, I'll still show my face next week then. Okay.
Sorry, can you please share Lab 5 in the chat? The
Oh,
link to Lab 5.
the link to lab 5. I'm coming. Check. I'm coming. Right. So have you checked the Google Classroom and it's not there? Our lab 5.
Yeah, it might not be there because it will probably be posted. It will probably get posted tomorrow.
Oh, okay.
Yeah. But I can let's see.
So do you want to post it now for in the class whole?
I will just put it here. Just 1 second.
Okay. Let's just wait a little bit.
I'm sorry, I dropped off for a minute.
Yeah, the link will be posted in the chat box.
Yes, but I dropped off for a minute and I just came back on, so I don't see it.
We haven't yet
Okay.
posted it.
Oh, you haven't posted. Okay, great.
Okay, sorry. It's on my computer, but it's far away, hidden somewhere. All right, so I'm having trouble putting it in the chat, so I'll have to just put it on the Google Classroom. So I'm posting it in the announcement, so it'll be easy to find. So if you just check on Google Classroom announcement, and maybe that then allows me to create the link that I can put
Okay, thank you. I see it.
in the chat. So I have a link in the chat, maybe you can download from there.
Thank you.
So if you are able to like download it, you can just significant so that we can move on for the R Labs section 5.
I have it now. Thank you very much.
Oh, okay. I believe everybody too should have it. So okay, today we'll be talking about chi-square actually, and maybe next week we'll be talking about comparing proportions and odd and all this kind of stuff like that. So if you're interested in like, okay, what chi-square does is that chi-square is a test of association or independency. When you want to check the relationship between two categorical variables. So when I mean two categorical variables, let's take gender, for example. We have male and we have female, and let's just say weight in category. We like kind of have a categorical variable. Maybe let's say weight to be very fat and slim and fat. So if you want to check relationship between the weight, like the categorical variable of weight, which is slim and fat, against the relationship against gender. So you want to see if there is relationship between gender and their body weight, maybe slim and fat, kind of like that. Or if you want to check gender and religion affiliation, kind of stuff. So it's a like test of association. So you, in this context of our example for this class, though you are interested in examining the relationship of severe mental distress and hours worked. So you can create, we are going to create a binary variable for hours worked, with 1 to represent hours greater than 80, and 0 0 like it's just like 0 to represent hours did not work. Okay, hours that is not up to like is not greater than 80. So we have 1 is hours, those who work hours more than 80, and 0 to be like hours lesser than 80. So, and we also define a cutoff for severe for mental health score, like distress severe mental health scores. We put a cutoff mark at 20. That is, if you have anybody who has a mental health score that is greater than 20, then we assign 1 to the person, and anybody that have lesser than that, we assign 0. So we have 2 categorical variables. In the hours work region, we have hours greater than 80 and hours lesser than 80. In the severe mental health distress, we have mental health score greater than 20 and lesser than 20. So now, if you want to check the relationship between these 2 categorical variables, it is ideal that we use chi-square to like test this relationship. Is it chi-square? Some people call it chi-square, some people call it chi-square. So chi-square to like check the relationship and association between 2 variables. So let's take a step backward. When we are talking about correlation, that correlation is the relationship between two or more variables, right? But correlation will not tell you like to what effect is one relationship. It just tell you the direction and the degree of linear relationship between the two of them. It will not tell you to one effect is to one effect or impact is the independent variable on the dependent variable. So just take chi-square as what is telling you the relationship between two categorical variables, but it will never tell you to what effect is one variable on the other. So if you want to check to what effect is one variable on another, then you have to like take a step forward to like logistics regression for that question, which we won't be talking about today. So chi-square can be calculated by hand. When you have like two tables, let's just say two table of like 2 rows and 2 columns against. So there is a way they calculate it by hand by finding we have the observed values, you find the expected values. So you subtract your observed value from the expected value, you square them, then divide it by the expected value. You don't have to worry yourself about that. So and okay, let's load our data, which is the resident doctor data. So we want to create a new variable called hours greater than 80. So that is, if the hours worked by the resident doctor is greater than 80, then you should identify it as 1. If it's lesser than 80, if otherwise, which is less than 80, you should categorize it as 0. Then we create another new variable called mental health score. If the mental health score is greater than 20, this new variable is called severe mental distress. So if it's greater than 20, you should categorize it as 1, and if otherwise, you should put it at 0. So now you use a cross tabulation. So you use tables. So if you write table, because we have this data set, if you check our data, what's the data again? Let's check the names in the data in the RDS now. So by now you should see we should have incoming. Then I did not run this line of code. If I run this and I run this, so and I come here to check names, we are going to see we have hours greater than 80 and we have severe mental health. So if you check, they are categorical variables, like they are 0 and 1, 0 and 1, they are in categories. So if you check the table, like you check the table, you create a table like by using the table function, then passing the variable names into the object, into this table function, we are going to have a table that shows the frequencies. So this is the frequency that shows that resident doctor who have mental health score that is lesser than 20 and who work 80 hours are just 13. Who work lesser than 80 hours are just 13. Those who have who work lesser than 80 hours and also have mental health score greater than 20 is 97. Resident doctor who work more than 80 hours but has mental health score lesser than 20 is 16. And resident doctor who work 80 hours and has mental health score greater than 20, they are 35. So you can just see the frequency, like the distribution across the groups. So to make it more informative, like you have to like add labels. So when you are saying if the hours work, we create another variable called hours greater than 80x. So this is, we just have to like put attribute. That is, if our hour cost is greater than 80, then attribute it not 1, don't give 1, just give greater than 80 hours. If otherwise, give lesser than or equals to 80 hours. Then we did the same for this. If the hours worked, if the mental health score is greater than 20, then attribute it to be severe mental distress. If otherwise, no severe mental distress. So when we run this, and you still check the names of the observation, if you check the names of the variables, names of RDS, we are going to see he has added the new variables we created already. So let's move on. So if you create the table too as well, the way we created the table earlier, and we are just writing this into this, so it makes some comment. Let me just clean this. Let me just leave this. So if you do this, you are going to have the percentage. Can you see the percentage? No, sorry, the frequency. So this tells you that resident doctor who work lesser than 80 and they don't have any form of mental distress, they are just 13. Those who work lesser than 80 and has some level of severe mental health distress, they are 97. So those who work greater than 80 with no mental health distress is 16. Those who work lesser than greater than 80 and have severe mental health is 35. These are just like frequencies. So now you can convert these frequencies into proportion. Let's write this into objects. Let's say table 1. Right? So if you pass this table, the table 1 like into a proportion, let's just say prop dot table, right? Let's just say prop dot table, and you put table 1. It's going to give you the proportion. It's going to give you the proportion. So, but you can calculate the proportion. Let me check something. So this is the proportion actually. So you can, if you want to calculate percentage from proportion, it's just by multiplying proportion by 100, right? So you get the percentage actually, the percentage of the distribution. The resident doctor, the percentage of resident doctor who works lesser than 80 hours and with no mental health distress, and you just get the percentage like that. Well, in this case, I know you'll be seeing this 1 and 2. So in this context, if you pass these proportion tables, if you pass table into the proportion dot table function, and you put comma 1, you want R to like calculate the percentage per row. Like you want R to use the rules to calculate the percentage. But if you put 2, it's going to calculate the percentage in column, like using the column. It's going to use the column sum to calculate the percentage. So what I'm saying is that if you notice, if you add these 2 together, you are going to have 100. If you add these 2 together, you are going to have 100. But if you add these 2 together, this row to this column together, these values of the column like 0.11 and 0.3, you will never have 100 because the first one calculates the percentage based on rows. Why this calculates the percentage based on columns? So I don't know if you get that, if you specify this 1 and 2, but you can just do that by just like, you can do away without using that by just saying proportion table 1, then you multiply by 100. So it's still the same. So depending on how you want to want it. But this like row percentage, it calculates the cell percentage. This is the cell percentage. It's going to calculate the cell percentage. So these are the cell percentage. And if you specify 1, it's going to calculate the cell percentage based on the rows. If you specify 2, it's going to calculate the cell percentage based on the columns. So now there is a function called chi sq test. So it takes some certain set of arguments. It takes x, it takes y, and some other arguments. So in this case, we want to like check the relationship between the hours worked and the mental health distress. Your null hypothesis is always saying that there is no relationship between hours worked and the level of mental health distress. Why your alternative will be saying that there is relationship between hours worked and level of mental health distress, right? So now, once you have this chi sq dot test and you specify your variables, the first variable is hours work x, right? Okay. Any way you do it, let's do severe dot this comma rds $, hours worked 80. So if you run this code, you are going to have your chi-square test, the test value, which is 7.71. This is the degree of freedom. How chi-square calculate the degree of freedom is that it minuses the number of rows minus 1 multiply by number of column minus 1. And in this place, we have 2 by 2, we have 2 rows, 2 columns. So number of rows, which is 2 minus 1, we have 1. 2 column minus 1, that we have 1. 1 multiplied by 1, that's how we have 1. So, and it generates a p-value. So it generates this p-value. So you can see that this p-value is far lesser than 0.005. It's lesser than 0.05, right? Which shows that there is significance, like we reject the null hypothesis and conclude that there is significant relationship between the hours worked and the level of mental health stress. So there is relationship between them, the hours worked and the level of mental health stress. So, but if you specify this function correct to be false, let's see what the function does. This argument does. Chi-squared test. Let's see. False. Correct. Let's see. So, this correct means that a logical indicating whether to apply continuity correction when computing the test statistics for 2 by 2 table. So, and maybe we set this to be false. So you see that there is changes in the value when it's at the default of truth, because I think it's at always default of truth. So, and default of false. But the p-values too, you still, like, if you set it as false, you still reject the null hypothesis too as well. So, and also you can get your chi-squared test by just, like, we have created a table called table 1. You can just, like, you can just use the summary function. Then you are going to still get the same thing. You are going to get the chi-square value. You are going to get the degree of freedom, and you are going to get the p-values. So, and this tells you that there is relationship between the hours worked and mental health, what I call mental health severity, like, and mental health distress. But what this will not tell you that to what effect is that relationship, that is what logistics is going to tell you. Yeah. So, is there any question? So, any question? So I think without any question, that is where we are going to stop for this week. So we hope next week, when we continue with logistics regression, I know you might have gone through the theoretical parts, like, of logistic regression. So we are going to dive deep into the logistic regression next week to, like, explain how to, like, quantify the relationship, to what effect is one categorical variable having on another, and all this kind of stuff using logistic regression. So thank you very much. Thanks for attending this section.
Thank you very much, Daniel.
So you can feel free to leave the class. So the class has ended. So